Jnanam Paramam Dheyam. Knowledge is supreme.
Right. So far we have discussed simple harmonic oscillator as a model for diatomic molecules, and we have learned what kind of energy levels we have in it. Now what we will talk about the wave function, and hence we are going to talk about the spectra. Again, you already know what the wave function is, so I will just write the result. The wave function is something like this: psi for V is equal to, of course, it is multiplied by a normalization constant. You do not need to know the form of that normalization constant. As long as you can write n, it is fine. Multiplied by e to the power minus alpha x square by 2, where x is what we had defined there. What is alpha? What is alpha? Root over k mu r divided by h cross. In most books it is written root over everything, and in the denominator you have h cross square. Do you have to remember this? No. I am sure I will forget this in a couple of days. You do not have to remember alpha equal to root over k mu r divided by h cross. If you require it, we will give it, but you should remember the general form of the wave function. Okay? Right, multiplied by, now we are getting familiar with the plot, multiplied by a polynomial, right. This polynomial is hv, and it is a polynomial in root over alpha multiplied by x. Okay, alpha is defined already. What are these polynomials called? Hermite polynomials. Excellent. Do you know the form of some Hermite polynomials? What is say h0? Yes, okay. I would say it is a constant, but one is a constant. What is say h1? h0 is 1, h1 is 1. This is kind of taking things a bit too far. It is the same as the variable, right? Right? What about h2? So, it is a second order polynomial. Just remember the order: 0th order polynomial, first order polynomial, second order polynomial, and so on and so forth. Okay? V determines the order of the Hermite polynomials. This is what you need to know, nothing else. And as you will see, this becomes rather important later on when we discuss vibration of polyatomic molecules, but that is still 1.5 months away. Okay, Hermite polynomials. And should I write it now? Should I write it later? I will write it now. Like our old friend associated legendary polynomials, these Hermite polynomials are also not unrelated to each other. They are also related to each other by a very similar kind of relationship. In this case, it is called Hermite polynomial identity. And this is how it is generally written. Let us say you write it in terms of some variable q. If you multiply a Hermite polynomial in q by the variable itself, then you get, now you are getting kind of getting used to this, you get v multiplied by h v minus 1 q, I think it is v plus 1 q, not that it matters, plus half h v minus 1 q. So, you are allowed to forget v and half, no problem, as long as you can remember a1 and a2, it is fine. So, like legendary polynomials, these Hermite polynomials are also, even though the name is Hermite, they are not hermits, they do not live in isolation, they are related to each other. Every Hermite polynomial when multiplied by the variable can be expressed as a linear sum of the polynomial before it and the polynomial after it. The polynomial higher than it, polynomial lower than it in the series. Very similar to your Legendre polynomials, and this would kind of give you a hint of what is going to follow, right. What is going to follow is a selection rule. Since we have discussed rigid rotor already, I think you can guess what the selection rule will be if you do not know already, right. But before that we still have to deal with this dipole moment. So, let us write first. How do I know which transitions are allowed, which transitions are not allowed? This is a recurrent question in this course, and the answer is also recurrent. I have to look at the transition moment integral. Transition moment integral, as you know by now, is yesterday I have written integrals. Today can I write brackets? Okay, thank you. Something like this, psi f mu psi I. Psi I is the wave function of the level of origin, psi f is the wave function of the level that is destination. Okay. Now, so before we proceed, we already know what psi I and psi f are. Okay. Let me see what mu is. How do I write mu? So, when we have a molecule and the bond length changes, should the dipole change or should the dipole remain the same? Provided there is a permanent dipole to start with, if you are talking about a diatomic molecule. In case of polyatomic molecules, there can be situations where there is no dipole moment to start with, but dipole moment is created during the course of vibration. Think of carbon monoxide. What does carbon monoxide look like? It is a linear molecule, right? Right? Now, does it have any dipole moment? No, because the bond moments are opposed to each other, right. But then suppose it vibrates like this is called bending vibration. Then what happens? In this case, the vector sum of this and this would be something like this. So, dipole is created. When it is here, the vector sum is like this. So, essentially for carbon dioxide, the dipole moment oscillates like this, right. We are going to discuss this in much more detail when we talk about polyatomic molecules. But for diatomic molecules, actually if you think of hydrogen H2, no matter how much the bond stretches, are you going to have a dipole moment? No. So, for diatomic molecules actually you need a permanent dipole moment, but we will see what the treatment tells us. So, let us write like this. Let us say the permanent dipole moment is mu 0. Of course, if there is no dipole moment, permanent dipole moment will be, well, mu 0 will be equal to 0 anyway. So, we work under the approximation that since we are talking about simple harmonic oscillator, what is the meaning of simple harmonic oscillation? Maximum amplitude is small, is not it? If the amplitude is too much, it is no longer simple harmonic. Remember the pendulum we studied in physics, what was the maximum angular displacement allowed for it to be simple harmonic? Yes, exactly 4 degrees. So, if it is 15 degrees, it is no longer simple harmonic. So, within that small displacement, you can assume, that is the wrong way to do it, to be something like this, mu 0 when x equal to 0, and then within that small range of x, you can consider it to be a straight line, okay. And if that is a straight line, what will my equation be? Mu will be mu 0 plus, I can write d mu d0, d mu dx at equilibrium position multiplied by x, okay. Are we clear with this? Slope multiplied by displacement, displacement starts from 0, okay. Now, we know this Hermite polynomial identity, and I hope we can erase this now. What is the transition moment integral then? It will be something like, I will just write it like this, psi v dash instead of dipole moment I am going to write mu 0 plus d mu dx at equilibrium position multiplied by x multiplied by say psi v. So, what kind of transition are we talking about? V to V dash. V is the origin, V dash is destination. Okay. So, right away I can write it as a sum of two integrals, can't I? So, the first one will be mu 0 is a constant or not? Mu 0 is a constant, so it comes out. So, I get it like this mu 0 multiplied by psi v dash psi v integrated over all space plus d mu dx 0. Can I take d mu dx 0 outside the integral? When can I take it outside the integral? When it is independent of x. So, if you work under this kind of approximation, then d mu dx 0 is independent of x, right, and we are saying d mu dx 0 anyway, which means it is very close to the equilibrium position. That comes out outside the integral, and inside you have psi v dash x psi v. Alright. Now see, can you say anything about this integral? That is 0 unless v equal to v dash, isn't it? Because psi v and psi v dash are members of an orthonormal set. So, this integral has to be 0 unless v equal to v dash, and if v equal to v dash, then there is no question of transition. What are we talking about? Okay. So, for the purpose of spectroscopy, for the purpose of transitions, first integral vanishes, and when it vanishes, it takes mu 0 along with itself, right. So, you see mu 0 is no longer important. It does not matter whether your molecule is highly dipolar or less dipolar, or well, even mu 0 equal to 0, you want to put it that way. As long as d mu dx 0 is non-zero, you are going to have IR activity. Okay, so far so good. So, I can erase this, you are left with this d mu dx 0. So, this then gives you the first condition, right, that this cannot be equal to 0. You cannot have a vibration in which the dipole moment does not change. Once again, it becomes more important when we talk about polyatomic molecules later on. Okay. Now, we can expand this thing a little bit. Let me just work with this part. What is x multiplied by psi v into root over alpha x? Well, I can write it as root over alpha x divided by root over alpha, no problem with that, and you already know what is root over alpha x multiplied by psi v of root over alpha x. What is that? It is, I will just write a1 a2, okay, a1 psi v plus 1, no sorry, what am I doing? I will write it like this. Let me do one more step. This is equal to 1 by root over alpha multiplied by root over alpha x multiplied by this Hermite polynomial hb in root over alpha x multiplied by e to the power minus alpha x square by 2. Is that right? I have just expanded the wave function. Alright. Now, I know what this is. I can use the Hermite polynomial identity, can't I? Question? Sure? Have you understood all the way? Alright. Now, I can use this Hermite polynomial identity, and I can write this is equal to, last bench, can you read if I write here? 1 by root over alpha, I will just write a1 and a2, a1 multiplied by hv plus 1 of root over alpha x plus A2 H of V minus 1 root over alpha x, whole thing is multiplied by e to the power minus alpha x square by 2. Are we okay? Yeah, can I explain what? Oh, see what do you have here? I am ignoring the bra vector, I am only working with the ket vector. In the ket vector you have x multiplied by psi v, and psi v is in root over alpha x. So, I am just writing that x multiplied by psi v of root over alpha x is equal to root over alpha x multiplied by psi v in root over alpha x divided by root over alpha, right. Root alpha by root alpha is just 1. The reason why I want it is, if I just take this 1 by root alpha out, I have root alpha x multiplied by a Hermite polynomial in root alpha x, right, which I know how to expand using the Hermite polynomial identity. Are we clear, or do you have a question? Are we clear what I am trying to do? So then we use the Hermite polynomial identity and I expanded this, and what I get is a sum of two terms, one in the Hermite polynomial of order v plus 1 and the other Hermite polynomial of order v minus 1, okay. Each is multiplied by e to the power minus alpha x square. So can I now write something like this? Can I erase this part? So that would be equal to 1 by root alpha A1 H v plus 1 in root x multiplied by e to the power minus alpha x square by root alpha x square by 2. What is that? Yeah, H v plus 1 multiplied by e to the power minus alpha x square by 2. What is that? This psi v, well psi v divided by n v, that is all, okay. I am not writing the normalization constants. So it is something like A1 multiplied by, well you can write B1 instead of A1 because there is another constant anyway, B1 multiplied by psi v plus 1 in root over alpha x, no I do not have to write that, I will just write psi v plus 1, and what is h v minus 1 multiplied by e to the power minus alpha x square by 2, that is psi v minus 1. I will write B2 psi v minus 1. In fact, I will even take this inside the constants, I am not writing what the constants are, right. So everything goes in B1 and B2. So now this is what this part is. So what is TMI? The transition moment integral boils down to d mu dx at equilibrium position multiplied by, in the bra vector you still have psi v dash, in the ket vector instead of x multiplied by psi v I can write b1 psi v1 psi v plus 1 plus b2 psi v minus 1. Instead of x into psi v, we have found out we can write b1 multiplied by psi v plus 1 plus b2 multiplied by psi v minus 1. Are we clear? What does that boil down to? Well, d mu dx at equilibrium multiplied by integral psi v dash psi v plus 1 plus, well there is a b1 here, b2 multiplied by integral psi v dashed psi v minus 1. When will the first integral survive? When v dashed equal to v plus 1. When will the second integral survive? When v dashed equal to v minus 1. So, what are the only two possibilities that come out from here? V dashed must be equal to V plus minus 1, or you can say delta V is equal to plus minus 1. This then is my selection rule for a simple harmonic oscillator, and additionally I get the condition that the vibration must bring about a change in dipole moment, otherwise it will not be IR active, right. If that is the case, what is the physical significance of selection rule is it tells you which transitions take place, which transition do not. For example, I will redraw this potential energy surface. Please accept that this is a parabola. Selection rule delta V equal to plus minus 1 tells me that this transition is allowed, okay. This transition is allowed. This transition is also allowed, downward transition. However, this transition is not allowed. Are you answered? Yes. Mathematics is the language of science, right. So, it tells us how the spectrum will look, if that is what you are asking. Physically, without doing mathematics, there is no way of well, actually there is. If you look at the wave functions and if you work with parity, then you can also say that odd even transition, see it is like this. What does this wave function look like? It is like this, right. What does this one look like? Something like this. What does this look like? Okay. So, are you familiar with odd and even functions? Is this an even function or an odd function? Even or odd? What about this? Odd. What about this? Even. So, alternately you have odd and even functions. Now, if you take this and this, now what will happen? This is an even function, this is an odd function. What about dipole moment, even or odd? Definitely odd, right. If you change x, mu becomes minus mu. So, now if I take a product of one wave function, another wave function and dipole moment, if these two wave functions, one is odd and one is even, then what will I have? Odd multiplied by even. So, odd into even, what is that? Is it odd or is it even? It is even. Okay. So, if I think of these two, the transition moment integral, well, the integrand is an even function. Okay. If it is an even function, then if you just change the sign, integral will not vanish. However, if you take this and this is what? Even. Your dipole moment is odd and this is also even. So, even, odd, even, what is that product? Odd. Now, see, if you are talking about V equal to 0 and V equal to 2, then your integrand is odd, right. That means, if you just interchange plus x and minus x, then what happens? Then it changes sign, integral changes sign, but then that cannot happen, right. If you just change plus x and minus x, if integral changes sign, that can happen only when the integral itself is 0, okay. That is why you cannot have this transition, but you can have this transition. Does this make sense? But see, even this is mathematical. When I talk about odd, even, integral not vanishing, even that is mathematics. It is just that it is a little, we are putting it in words, that is why it seems less mathematical and more, well, physical to us. Actually, it is all the same. Okay, this is more rigorous mathematics, this is less rigorous. Why I am saying this less rigorous is this: by this argument, can you say that from here to here the transition is not allowed? You cannot, right? Because see, this is even, odd, even, this is also odd. So, how do you know that 0 to 3 is not allowed? You cannot, because we have performed a more qualitative, less quantitative argument. We can only say transition between odd and even will take place, but what we have done is a more rigorous mathematical treatment which tells us that this is allowed, but this is not allowed, alright. But wait for maybe 2 more minutes, perhaps you will be answered in a little better way. Now see, delta V equal to plus minus 1. If you remember what we had said, what is EV plus 1 minus EV? Yeah, H nu Vib, where nu Vib is the frequency of vibration, root over k by mu r, right. Now, if this transition is allowed, then now I have made it very complicated. This transition is allowed, we are saying. So, that means if I put in light, let us say frequency of light is h nu light or h nu p, p for photon. Can we live with that, h nu p? So, h nu p, what is nu p? What is nu p? Frequency of the photon or frequency of light, that is equal to the energy gap, right. Which condition is that? Bohr resonance condition. So, what you see is Bohr resonance condition leads to h nu p being equal to h nu Vib, and of course, it is simple mathematics to eliminate h from both the sides, and you come up with this. I find this to be very amusing. Frequency of the photon must be equal to actual frequency of vibration, which is equal to 1 by 2 pi root over k by mu r, so that the photon is absorbed. Frequency of light has to be equal to frequency of oscillation, then and then only we are recording, then and then only it is going to be absorbed. What kind of spectrum do we expect in that case? How many lines in the spectrum? 1. Right? You expect one spectrum. Do you get one spectrum? Actually, if you get, do you get one line? If you have a bad spectrometer, then yes, you get one line. If you have a good enough spectrometer, a spectrometer with high enough resolution, then you get a spectrum that looks like this. So, next day we are going to continue from here, and we will discuss why, if you have a good spectrometer with enough resolution, this one line becomes shows up actually this two wing kind of structure, and then we will talk about your anharmonic oscillator.